Okay, so this is recording now. This is going to be the not homework review session, but the exam review session. It should last 2 hours, and we're going to go over just some general questions, general concepts that you guys have issues with. Namely, so far it's going to be torque, work, work energy theorem, and then there's bending as well. So I'm not sure exactly what aspect of bending we can go over, but we can just, I guess when we get there, we'll kind of figure it out. And then we have some exam problems from the practice exam that we'll go over with, namely number 2 for the written response, and then problems 5, 14, 16, and 17 on the multiple choice. So first of all, with torque, bending is like the last, like literally last week's stuff, which is like, if you think bending coefficient, Young's modulus, like the elasticity stuff, basically. Yeah, week 9. So I'll start first with like the torque concepts. So, I mean, very like, I'll just go right into it. So we have torque, right? Torque, the way we define torque or think about it is the ability for an object to rotate, right? So the capacity for that object to rotate. Now, torque is dependent on a couple things. First of all, it's dependent on a force applied, right? It's also dependent on how far you apply that force relative to a specific pivot point, right? How far you apply the force relative to a starting point, and then the angle at which you apply that force, right? And that's defined as sine phi, right? Sine of the angle at which you apply that force, right? That's gonna impart a specific torque, or it's gonna give an object the capacity or ability to rotate, right? That's the concept of torque, to be able to give an object the capacity to rotate. Now, for torque, we have this equation Fr sine phi, right? Now, the issue with this stuff right here with torque is the notation for having negative or positive torque kind of differs from your normal, I guess, notations for forces. So for forces, you're used to, okay, if a force is along the positive y-axis, let's say force normal, for example, it's along the positive y-axis, that's a positive force. Oh, if it's along the negative y-axis, like Fg, for example, that's a negative force, right? Positive, negative, positive y-axis, negative y-axis. You also have forces along the positive x and negative x axes, right? So that's kind of, that's logical, that makes sense. Now, the issue with torque here is that it's not based on like positive or negative axes and stuff like that. It's based on whether you're going clockwise or counterclockwise when you're applying the specific force. So if we have a rod, right, and the easiest way to think about whether something's going clockwise or counterclockwise, other than just like thinking of a clock, is if you're midway through the exam and you kind of forget what's going on or how to look at what kind of direction the force is going to be causing a rotation in, then you can just literally just grab your pencil, right? So if we imagine this is a pencil or this is a rod, right? If we were to hold the pencil at the eraser, kind of at the end here, right? And we were to apply a force like this, upwards, well, you can see that that pencil is going to go upwards to the left like this, and that would be counterclockwise, right? Counterclockwise. Now, if I were to apply a force like this, downwards on the pencil, well, the pencil is going to move downwards and to the right instead of to the left, right? And that's going to be clockwise, right? And that makes sense. Like if this was a minute hand or an hour hand on the clock, right? If we go this way, this way, this way, this way, we're going forward in time, right? We're going forward in time. So we're going clockwise. If we were to push the pencil or the minute hand or the hour hand this way, right, upwards and to the left, we go this way, this way, this way. We're going backwards in time, counterclockwise. Now, with torque, the idea is that counterclockwise is denoted as, or actually, I'll do a colon instead, is denoted as positive torque, right? Clockwise is denoted as negative torque, right? So it's kind of counterintuitive in the sense that you'd think that, okay, if I'm moving clockwise, I'm going forward in time, I'm increasing time, okay, well then that's positive, right? And you would think that counterclockwise, it's the opposite direction, right? Should be negative, but it's actually the other way around. If you're going counterclockwise, we denote that as positive torque. If you're going clockwise, we denote that as negative torque, right? So that's how you get the direction for torque. Torque, the direction for it, right, the sign, positive or negative, is only dependent on whether the overall object is going to be moving counterclockwise or clockwise based on the force applied. The force that we put here and the radial line that we put there, right, the distance away from the radial line, that's all going to be positive, right? Your force is positive, your radius is positive, and your sign, right, that you apply, or your angle, right, sine phi, that's going to be all positive. Whether you add a negative or not depends on if you're moving clockwise or not, right? Now, r is the distance from the radial line. And so we define, if we have this rod right here of this pencil, right, we have to define a pivot first. So pivot here, for example, this is where we're holding, this is like our hinge, this is where we're holding the pencil, right? So any distance away along the length of the rod, along the length of the pencil, along the length of the object, any distance away along that length, right, that's going to be the distance along the radial line, right? So if we think about radial like radius, right? So if this is the radius, for example, this is a horribly drawn circle, but this is the radius, right? Then any point here is a point along the radial line. So if I chose this as the center of my circle, here it might be 1 centimeter away. Here it might be 2 centimeters away. Here it might be 3. Here it might be 4, right? So based on where the force is applied, right? If it's applied here, for example, then I might say, okay, well, it's applied 4 centimeters along the radial line, or away 4 centimeters away from the pivot or the hinge, right? Now, the key here where a lot of people get tripped up is the angle. How do you determine the angle? And the angle is determined by, this is the easiest way to think about it, it's determined by the angle that's sandwiched in between the radial line and the force applied. So if I have a force applied like this, right, directly perpendicular to the radial line, literally just straight up upwards, then this forms a 90-degree angle, right? Now what if I were to apply a force at an angle like this, right? What if I would apply an angle like this? Well, the angle then that I use is this one, the one that's sandwiched in between the force that I'm applying here and the radial line here. So the arc that you draw, the little arc that you draw for the angle should be touching both the force and the radial line. So you can see here it touches the radial line and it touches the force, right? Forms a little, you can think of it as forming a little W here, right? Now, it can also be this angle, for instance, because it's still touching here, but usually it's just, this is the one that we use kind of. I mean, either way, this might be, if this is like, I don't know, like if this was 30 degrees, right? Then this would be 150. Sine of 150 is the same as sine 30 degrees, right? Doesn't matter. Now, where people might get tripped up is that if the problem says, for example, that, oh, the force was applied 30 degrees from the perpendicular or from the vertical, right? Then this is the angle that they're referring to, 30 degrees from the vertical or 30 degrees from the perpendicular. That's not the angle that we use, because this angle right here is only touching the force, right? Our radial line is down here. So instead, if it's 30 degrees from the perpendicular, if this is the perpendicular, this whole thing forms a 90-degree angle, right? This is all 90 degrees. If it's 30 degrees from the perpendicular, then it might be like this. This is 30 degrees. Well, that's the angle between the perpendicular and the force, but it's not the angle between the force and the radial line. So we have to take 90 minus 30, that's 60 degrees, and that's the little angle that you get here in the arc, right? The little arc here is 60 degrees, for instance. So it's always the angle that's sandwiched in between the force and the radial line. R here is the distance away along the radial line from the pivot or the hinge, right? And the force here is just the force that you apply, right? Counterclockwise is positive torque, clockwise is negative torque, right? That should kind of sums up what's going on with torque and how to calculate it. Now, if you're calculating positive, or when you're calculating net torque, right? Well, you just add up all the torques that you have, right? So when you add up your torques, if the first force is applying if the force, this right here, is applying in a direction that's counterclockwise, well, the first force is going to be counterclockwise, that's positive, right? Torque 1, force 1, it's a positive torque because it's counterclockwise. Now, if I were to look at this force right here, well, it's making the object turn clockwise, so it has a negative torque, right? So we can subtract those two together to figure out our net torque. Now, the thing is, if I were to, for example, have my pivot in a different location, if I had my pivot right here, and I applied a force like this, right? Well, then this is moving counterclockwise, right? If I hold the pencil in the middle and I push this way, right, or this way, right, it's going to go counterclockwise, up and to the left. Now, if I push this way, right, if I pushed this way, then it goes up and to the right, and that's clockwise, right? So I literally just have to imagine what's going on, right? If I had something here, like a hinge right here, if I had my pencil, if I was holding it in the middle, if I pushed up this way, then this goes clockwise, right? If I push this way, this goes counterclockwise, right? So it's not about memorization or anything like that. You have to just take step by step, look at where your hinge is at, where the force is being applied, and what kind of directions those forces are going to cause on the object itself, right? So that's the main issue there with regards to direction and torque. Now, at the same time, what was I going to say? So there is a concept of static equilibrium, right? Static equilibrium has two conditions. Static equilibrium has two conditions, and those two conditions are F net has to be 0, so all the forces have to cancel each other out, and the torques have to cancel each other out, right? So theoretically, right, if I had, yeah, go ahead. Yeah, I mean, if you have any object, right, and there's forces or torque being acted on that object, right, it doesn't matter as long as they're exerting some kind of force or exerting some kind of torque, right? And the object is stable, it's not moving, it's not rotating at all, right? Then there's static equilibrium if all the forces cancel out to be 0 and the net torque is 0, right? So whether uniform bar or not, right? The idea here is that if I'm applying, for example, a force like this here and another force here, right? Well, then I have to have the torques cancel out, right? So they have to be, this one might be clockwise and this one is counterclockwise, but the calculations for the torques, right? Fr sine phi, when I calculate for them, they have to be equal and opposite to each other, so there's no net torque. And at the same time, there should be canceling out of the forces. Well, do you see any canceling out of the forces here? If both forces are pointing upwards, if we were to write an F net equation, then they're both positive forces, F1 plus F2. There's no net forces equal to 0 here. Now, say for example, there is no movement that we observe. Then theoretically, there would be a third force pointing downwards, for example, on the pivot, theoretically, right? That would cancel out the sum of both of these forces. Sum of both of these forces. So if you were to write an F net, it would be like, okay, well, this is F1, F2, and there's F3 here at the pivot, right? So F1 plus F2 minus F3, and that's equal to 0. So there's no net force, right? And then if you were to calculate the torques, if the torque due to force 1 and the torque due to force 2 cancel each other out, then you're good. Force 3, on the other hand, right? Force 3 would be exerting no torque because if you think about, once again, r is the distance away from the pivot. So if you're acting a force at the pivot, r is equal to 0. So there's no torque. Torque 3 is equal to 0. So as long as the torques for these two forces cancel out and the forces here that are acting cancel out, then you have static equilibrium. So, okay, but since someone says, since the pivot is in the middle, why wouldn't the two forces cancel out? So like, the forces can't cancel out because they're both pointed in the same direction. These are both along the positive y-axis. So if we were to write a F net equation, it would be F1 plus F2. So there must be a third. That's assuming we see no movement in the rod at all. Then there must be a third force, and that third force could be acting at the pivot, for example. That would be in the opposite direction, right? So F1 plus F2 minus F3, and that would cancel out the other two forces here. Yep. The torques would cancel out. The torques would cancel out. But the forces haven't because they're both pointed in the same direction. Yep. Yeah, it's the two conditions that have to be met. You have to have both the torques cancel out, right? And then net force has to be 0 as well for static equilibrium, right? That's the other thing about torque. I think that covers generally like the big main topics about torque. Anything else you guys have questions about with regards to torque? I don't know if there's anything else off the top of my head. Mm-hmm. So yeah. So your torque is dependent on the angle, and well, okay. So whether torque is positive or negative only depends on the direction that the rotation is in. If it's counterclockwise, it's positive. If it's clockwise, it's negative. But your forces, they could be negative along the negative y-axis or positive along the positive y-axis, right? And then if you have static equilibrium, they cancel out. F net has to be equal to 0. So torque is only dependent, like the sign for it, the sign for torque is only dependent on whether you're going counterclockwise or clockwise. Otherwise, the magnitude of torque will be dependent on the force, but not its direction, right? We don't care about the direction. We don't care about the direction of the radial line as well, right? It could, if the pivot is here, we don't say that this is negative 3 meters, for example, or this is positive 3 meters. It's just the magnitude of, or the absolute value of the radial line, magnitude or absolute value of the force, right? And then sine of the angle that's sandwiched in between the force and the radial line. And then we add a positive or a negative basically at the end, based on if it's going counterclockwise or clockwise. Yeah, so how to determine clockwise and counterclockwise if there's a beam with supports. So once again, it's just kind of like imagining what's going on. So if we have a support here, support there, or at least, you know what? Okay. So I don't know if we want to, we'll do one support first and then we can do two supports. But basically, whether it's moving counterclockwise or clockwise, it's like whatever your support here is, think about your pencil. If you pinch it here at the middle, if you push downwards like this, if you literally, like all of you just grab your pencils right now and push downwards, like hold the pencil at the middle. I'm doing it right now. Hold the pencil in the middle, right? Pinch it in the middle and then push downwards to the right, right? So apply a force to the right. So if you see that force there, it's gonna push down the pencil this way, right? So on a clock, if you go from here to here, you're going forward in time, and that's clockwise, right? If you pinch the pencil still here, that's your support, right? And you push downwards like this, right? Well, let's do it again. I pinch in the middle, right? I pull downwards to the left there, then I'm going this way. I'm going downwards this way, like that. And that's what? That's counterclockwise, right? Now, if I push upwards like this, once again, if I pinch the pencil in the middle, right, here, if I push upwards, then I can see that the eraser end of the pencil is going to go this way, this way, this way, this way. That's clockwise, right? So if I push this way, it's going to be clockwise. Now, if I push, for example, here on this end as well, right? If I pinch the pencil in the middle or the beam in the middle, right? I can think about it this way. Then if I pull the pencil upwards like this, then I can see that it's moving counterclockwise, right? Now, if you were to have like two supports, for example, here and here, right? Then if I push downwards here, well, I think about, okay, if I pinched my pencil kind of in two places almost, which is kind of hard to do, but if I pull downwards, or I can imagine if it was a diving board, right? Diving board kind of tilts downward like this from your weight. So if that was like a minute hand on a clock, right? It goes downwards forward in time. So force pointing downwards like this would be clockwise, right? So that would be negative torque. If, for example, someone were to push the diving board upwards, so it curves up like this, right? And that's going backwards in time, that's counterclockwise. Now, if the support was also kind of shifted to the right a little bit like this, if there were two supports, for example, same idea. You push downwards like this, you can see that the pencil or the beam or the diving board or whatever kind of rotates this way. So it goes downwards like this, right? So that's counterclockwise. This is counterclockwise. If I push upwards like this, right, then the beam kind of goes forward in time. So this one would be clockwise. So hopefully that kind of explains a little bit better with beam and supports. Does that make sense? If you were to pick a pivot, so like if I just chose, for example, okay, so I mean, it just, once again, like whatever pivot you pick, like if I picked a pivot here, for example, it's the same idea. I just pinch my pencil in the middle here and I pull it up to the top. So if I pull the pencil upwards like this, I'm going backwards in time. So that's counterclockwise. If I pull it downwards like this, then it's clockwise. Same concept applied to the left side. And even if the pivot was changed, right? If it was here, for example, you kind of apply that same concept in vision, right? So, but yeah, I mean, regardless of where you put the pivot at, it's just a matter of like kind of thinking about using a pencil. If you were to use the pivot as the place where you pinch the pencil at and you pull upwards or pull downwards on the pencil, you can look at as if it was a minute hand on a clock. Okay, what direction does that move in, right? Does that move the minute hand upwards and to the left, kind of counterclockwise, right? Or does it go downwards and to the right, clockwise? Does it go forward in time, backwards in time? But yeah. Sound good? Any other questions about the torque stuff? Okay, I will erase. The other equilibrium, right? You could have dynamic equilibrium. So dynamic equilibrium is basically like where one of those conditions isn't met. So I could, for example, have let's see here. So yeah, I mean, honestly, I could have one of the conditions not met. So maybe F net is not equal to 0, right? But my torque is. So in this case, that you might see like, I guess like, let's see, I'm trying to think of a good example there. So if you see no net torque, then you're not observing any rotation. And so you might have a force maybe just giving translational motion, for example. So yeah, I think it's just one of the conditions isn't met, I'm pretty sure. But usually you'll just see the static equilibrium stuff where the torque is equal to 0 and the F net is equal to 0. But yeah, I mean, in general though, dynamic equilibrium is like usually if you have an object, for example, like moving at a constant speed, so the F net is equal to 0, where like you're still observing motion. That's why they call it dynamic, right? So you're still observing motion. It's just that maybe you're moving at a constant speed, so there's not necessarily like, I guess your net force would be equal to 0 because there's no acceleration, but you're still in motion. So I guess forget maybe the torque stuff for dynamic equilibrium. Just think about like if your object is in motion, just that there's no net force though. So like F net is equal to 0. V is constant. It's not constant 0 meters per second. It might be constant 30 meters per second, to where you're observing 0 acceleration, zero net force, right? But you're still in motion. That's why they call it dynamic. So that's what I think about for dynamic equilibrium. But like I said, for torque and stuff, you're going to be focused on static equilibrium, which is just that the object is stationary, and then these two conditions have to be met. But yeah. Sound good? All right. I'll erase this stuff here real quick. And then I'll move on to energy. So energy, right? Energy, for the work energy theorem stuff, it's just this right here. So we have work is equal to change in energy, right? Now our change in energy is usually equal to the sum of the different types of energies that we have, or the change in the sum, or the sum of the changes of the types of energy that we have. So there's kinetic energy, there's gravitational potential energy, for example. There might be spring potential energy, right? There might be thermal energy as well. So it's just the sum of the changes in the different energies that we have, right? That's our change in energy. Now, the change in energy, right, the side of this equation will depend on a couple things. So number one, what you see here on the right depends on if you're internalizing or externalizing certain forces. And it also depends on what the situation is specifically. So, for example, if we don't have any spring, we shouldn't expect to see any spring potential energy, right? If we don't have any friction, right, assuming we're internalizing all our forces, then we don't expect to see any thermal energy, because there's no friction, there's nothing, there's no energy generated, no thermal energy generated by friction, right? So no thermal energy, no spring potential energy if we don't see any spring or a rough patch or something like that, right? Now, kinetic energy is present, right, if there's motion. Gravitational potential energy is present if there's specific height or a change in height, for example. Now, with internalizing versus externalizing forces, right, internalizing forces is going to be the idea that if we were to blow up a free body diagram, so normally you just look at a free body diagram as a circle, right? If we were to blow this thing up, look at the inside, right? If we're internalizing forces like gravity, right, internalizing forces like friction, whatever, it allows us to calculate for the energies associated with those forces. And those are the energies that you saw earlier to the right side of this equation, right? So if I were to internalize the force of gravity, make gravity part of my system, gravity, instead of being a force that you would normally draw on the free body diagram like this, as a line outside of the circle, it's no longer a line outside of the circle. It becomes inside. It's part of the system. So when it's part of the system, it's internal. It allows us to calculate for the type of energy associated with that force. So the force of gravity, the energy associated with it is gravitational potential energy, right? So if we were to internalize the force of gravity, it's no longer external. We can calculate for the energy associated with that force, which is gravitational potential energy. And then obviously we have kinetic, for example, if there's motion, right? So in this case, right, if all our forces are external, or my bad, if all our forces are internal, everything is internalized, we can calculate for the energies associated with those internal forces, then there are no external forces, and the change in energy is zero. So when everything is internal, work is equal to the change in energy, and that's equal to 0, right? Energy is completely conserved, and in this specific type of condition, we call it a isolated system. It's completely isolated. No other external forces are acting on it, right? Now that's going to be the sum of the change in kinetic and the change in gravitational potential. Now, for externalizing forces, if we were to externalize the force of gravity, instead of being internal inside the circle, we make it outside, like before, right? As a line outside of the circle, force of gravity external. So in this case, right, force of gravity external, then the force of gravity would be exerting or doing work, my bad, not exerting. So, we'd have a force doing work, right? This force of gravity would be doing work, and that's equal to the force, right? Force of gravity times the distance at which that force is applied times cosine of the angle between the distance or the direction of motion and the force applied. That's cosine theta, right? Now, an example of this where you'd externalize, right, or when you can externalize, is if the angle is constant, right? So if I have the direction of motion is like this, directly downwards, and the force of gravity is directly downwards, right? Then the angle between them is 0. They're directed along the same plane, along the same direction. So it'd be cosine 0. Cosine 0 is 1. So in order to find the work done by gravity, I just take the force of gravity multiplied by the distance at which that force was applied, and then I can get work. Now, almost always you're going to want to internalize forces of gravity and be able to calculate for the gravitational potential energy, and I'll explain here why in a sec. And yeah, the angle would be 0. Now, I see some questions here in the chat, my bad, that I overlooked. For gravity, or whether figuring out where or when you need to use specific energies is dependent on what's present in the system. So if we start off at the top of a hill, for example, there's a specific height, and we end up at the bottom of the hill, right? There's a change in height, right? There's a change in height. If there's height, if there's position, right, then gravitational potential energy is a energy that we would have to calculate for example. If there's a spring, right, that you bump into or that you compress, then there's spring potential energy associated with that example. For, like I said earlier, for an example of when gravity would be external to the system is that, you in any case, you can technically externalize the force of gravity. It's just that whether or not you do so depends on the nature of the problem and how easy it is to externalize or internalize gravity. Almost like 99% of the time you're going to want to internalize it. It's just so much easier to do so. Because if I were to for example, if I had to have a hill, right, like this, and let's say, like, here's actually, so if I do this flat like this, and here's a slope, here's another flat portion, right? If I wanted to calculate the work done by gravity, right, if I want to externalize gravity and calculate the work, well, then I have to calculate the force of gravity here, right? And the distance here is this way, right? That's a perpendicular angle here. That's a 90-degree angle. The work from point A to point B, because force of gravity and the distance are exactly forming a right angle, the work over this interval is 0. How about from point B to point C? Well, in order to figure out what the angle would be, well, force of gravity always points downwards, right? My direction is this way along the slope. So I'd have to find out what this angle is. Say, for example, if this angle here was different too, I'd have to find out the angle there as well, right? So unless they give you that angle, it's going to be impossible to externalize the force of gravity. The only real time where it's easy to do so is if you have the direction and the force of gravity, for example, pointing in the same plane or same direction. So in that case, cosine 0 would be 1. Or if they're directly opposed to each other, like this, for example, then that would be cosine 180, which is -1. So I would just say almost always it's better to internalize. Externalizing, you have to keep track of the angles and stuff like that, and that's just going to be a hassle. So for the external perspective, though, whether you're going internal or external, energy is conserved. So you might think, well, here W is equal to delta E is equal to 0, right? Well, here W is equal to this is equal to delta E, right? There's some value here. So if this is 30 joules, then the change in energy is 30 joules, right? The change in energy is 30 joules. Well, then you might think, okay, well, energy isn't conserved here, right? Well, the thing is, it is. From an overarching perspective, law of conservation of energy is that energy cannot be created or destroyed. It's just lost or transferred, right? So with the internal perspective, everything is part of the system, right? So the idea here is that if we were to observe a person skydiving, right? Person is starting at a height of 300 meters, for example, and they end up at 0 meters. And here's the different heights in between, 200, 100, for example, right? Now, you start in the helicopter, right, at rest. So your initial kinetic energy, because kinetic energy, remember, is half mv squared. You start off at rest, so you're not moving, so your initial kinetic energy is 0, because your velocity is 0, right? Logically, as you jump out of the plane, right, and you go through the air, you're going to start speeding up, right? So your v is going to increase. So let's make the 100-meter point our kf, right? You might be traveling at a certain speed at this 100-meter position, which is going to give you a change in kinetic energy, right? That's what we observe. Now, if we didn't know any physics, if we didn't understand what gravity is, if we didn't understand what potential energy is, right, all of that, if we were just observing what is occurring, what's occurring is that this person is crazy and they're jumping out of the helicopter and now they're speeding up. How can I explain that speeding up? How can I explain that change in speed? How can I explain that change in kinetic energy? That's the idea here, whether you choose the internal or external perspective. Both of them tell us that energy is conserved. It's just that they say it in different ways, essentially. So for the internal perspective, we can see here that there are no external forces. Everything is internal to the system. Force of gravity is internal. Therefore, we can calculate for gravitational potential energy. So we see that the change in energy is 0, right? There is no change in energy, right? But you might think, well, if we sped up, we went from 0 kinetic energy to maybe 300 joules of kinetic energy, right? For example. Now, for this internal perspective, whatever change we see here, the change in kinetic energy, is equal and opposite to the change that we observe in gravitational potential energy, right? So if we were to, for example, just real quick, look at the initial starting point here. At this height, since we're not moving, we have 0 kinetic energy. But we do have potential energy, right? Because we're at a specific height. That would be equal to mgh, or mg times 300 meters. So let's say that's 300 joules at this top point. By the time you get to 100 meters, you might have decreased to 200 joules, right? So that's an overall decrease in your gravitational potential energy. Delta UG is equal to negative 100 joules, right? Now, you lost 100 joules here. Is it lost permanently? No, because we know that energy is conserved by the law of conservation of energy, right? So where does this 100 joules have to go? Well, if energy is conserved in the internal perspective of the equation, there's no change in energy. Change in energy is equal to 0. Well, if this is negative 100, right, then this has to be positive 100 to cancel it out so that you have 0. Well, what does that mean exactly? The way I think about it is that to explain the change in speed that you observe from the top of the helicopter to this 100-meter point, that change in speed is caused by the energy that was sucked out of gravitational potential energy and then was sucked into kinetic. So if we started off with an initial kinetic, like I said earlier, with an initial kinetic of 0, right? And I went from position 300 meters to 200 meters, the fact that my position changed caused a decrease in my gravitational potential energy of 100 joules. Those 100 joules aren't lost forever. They're simply transferred into, they're sucked out of gravitational potential energy, sucked out and pumped back into kinetic, right? So if I see a decrease of negative 100 joules here for gravitational potential energy, I should see an equal but opposite increase in my kinetic of 100 joules, right? That's what I should be seeing. That's from my internal perspective. From my external perspective, what I can see here is that there's work being done by the force of gravity, right? Force of gravity now is external. So when force of gravity is external, like I said, then we can no longer calculate for gravitational potential energy, right? It's not inside the circle anymore. So, The only thing here on the inside would just be kinetic, and force of gravity is external, right? Force of gravity is exerting work now. So I can find out the work due to gravity, multiply the force of gravity times d cosine theta, right? Figure out the work. That's going to give me a change in energy, right? So since we know that the angle here is 0 because the force of gravity is pointing in the exact same direction as our distance, right? Then we're going to see here a positive work, right? A positive work. So this might be an increase of, well, let's keep it consistent, an increase of 100 joules, right? And that's going to be a change in energy of 100 joules. Well, since we know that for this external perspective, since we're externalizing gravity, we can no longer calculate for gravitational potential energy. We cannot add it to the right side of the equation. So you're only left with change in kinetic here. So this external perspective, as you can see, tells us that, okay, work done by gravity is 100 joules. It imparted a change in energy of 100 joules or added 100 joules of energy to the system. And that caused a positive 100 joule increase in kinetic energy. Well, that's the exact same thing as we saw as internal, right? We still saw a 100 joule increase, right? Remember I wrote over here 100 joule increase for kinetic. Kinetic initial was 0. Kinetic final was 100 joules, right? There was a 100 joule increase. It's just that the way we describe it is different, internal versus external. For here, we say that the energy is kind of sucked out of one type of energy and pumped back into the other. And then here we say that, okay, an external force added energy of 100 joules to the system, right? It added energy of 100 joules to the system. So you might think now, okay, well, how is adding energy here, right? Still making sense with the conservation of energy, right? Because we said energy cannot be created or destroyed, right? Well, if there's an addition of 100 joules here, and that explains our change in speed and our change in kinetic energy or our increase in kinetic energy, well, that 100 joules, right? If we were to go back to that internal perspective, or if simply we learned about gravitational potential energy and we calculated for the difference in gravitational potential energy, then we can see here that, okay, well, the gravitational potential energy decreased by negative 100 joules. So if we add up the work that gravity did back to that change in gravitational potential energy, we can see that it's 0, right? And the same thing, especially if you have usually this internal versus external stuff, you'll see it with friction, right? Because friction, we're going to normally use the external perspective because we can say that, okay, work done by friction, right, is equal to the friction force, let's say F kinetic, for example, times the distance at which it was applied, cosine 180, for example. Usually it's cosine 180 because it's acting opposite to the direction of motion. So this might impart a change of negative 30 joules to our energy, right? So if I was moving along and I found a rough patch, I was traveling 30 meters per second, and then after the rough patch, I'm at 20, then my speed decreased, right? I slowed down because of the friction due to the rough patch. So if I were to calculate that change in kinetic energy, right, the change in kinetic energy, it might be that decrease of 30 joules, that negative 30 joule decrease, right? So I can say that, okay, well, the friction took away 30 joules from my system. It took away 30 joules of my system. Now, if I were to go back and look at kind of like the internal perspective, right? So if I have work is equal to delta E is equal to 0, well, if I'm traveling over a level surface, right, I'm not changing my height, then gravitational potential energy is equal to 0. But I slowed down, right? So I should see that same negative 30 joule decrease. Well, how is delta E equal to 0 if you have negative 30 joules on the right here? Well, the thing is, for friction especially, this is the external perspective of friction. For the internal perspective of friction, we think about it as, okay, well, work is equal to delta E is equal to 0. Again, because this is an isolated system, there are no external forces. And we can say that, okay, well, we observe a change in kinetic energy because of the change in speed. That might be negative 30 joules. If we're traveling over a level surface, there's no change in height, so that might be 0. Well, how do we explain this negative 30 joules? How do we explain the decrease in speed? Well, we can explain it the way here. There is thermal energy generated. There's heat essentially generated by friction. And that thermal energy, right, that heat generates positive 30 joules. So this negative 30 joules plus 30 joules is equal to 0, right? So you can see here that energy is conserved here, right? So energy is always conserved. It's just based on the different perspectives, right? We might need to go add back the 100 joules here, for example, to the decrease in 100 joules that we saw for gravitational potential energy. If we saw a negative 30 joule, work being done by friction, then we can add that friction back as a increase in the thermal energy to the decrease that we saw in our speed and our kinetic friction, or kinetic energy, my bad. So energy is always conserved. Whether we choose internal or external depends on how we want to describe what's going on. Usually, almost always going to want to go with the internal perspective route because it avoids using the angle stuff, especially if the angle is not constant, right? So almost always you're going to use internal perspective of things. External usually comes in handy if you're doing friction, because if you use the thermal energy stuff, it's going to throw you off a little bit. So you can just say that, okay, well, friction took away basically like 30 joules from the system, right? And then we can kind of see how that affects the change in kinetic or change in gravitational potential energy or whatever. But yeah, that's the main idea for work. If you understand the idea of internalization versus externalization, you should be good. But yeah, it's kind of a tough concept to wrap your head around. And there's a question in the chat here. If you're given mu for friction, do you always include it in the friction calculation? Yes, because if you are calculating kinetic friction, for example, and you know the normal force, you can say mu times Fn, and that gives you your kinetic friction, for example. But if you're given the force of friction automatically, then you don't have to include mu. But yeah. Any questions about this energy stuff? Nope. Okay. I think the last thing that we had to cover in terms of like concepts was the bending stuff. But really the bending stuff is like mostly calculation based. So whoever asked that, do you have a specific question about the bending stuff? Because I'm not really sure where to start because there's just a lot of equations. So yeah, if you want to go ahead and suggest maybe like a specific idea or concept that you're a little bit confused about, because honestly this bending stuff is mostly just keeping track of the equations. And we can do I have a couple problems here that will go over the bending stuff. But yeah, okay, if you have a problem, yeah, honestly we can just go over it. So we'll do problem 19, and then someone earlier had a couple questions like number 5, 14, 16, something like that. But for number 19 here, so 19, this is just a spring, right? So this isn't necessarily like the bending stuff per se. This is, well, I guess it was covered again in the last week's stuff, but it's primarily, I think, from earlier when we were doing, or actually no, hold up. Yeah, it was when we did energy. That's when we did it. So, for this problem says it takes 3 joules to compress the spring 2 centimeters from its equilibrium position. So 2 centimeters from its equilibrium position, that gives us a delta L or an X, right, of 2 centimeters, or that's 0.02 meters, right? When the spring is compressed to 4 centimeters from equilibrium, how much potential energy will be stored in the spring? Well, the idea here is that you probably don't even have to calculate it out, because this is just telling you, okay, well, if 3 joules is equal to half kx squared, right, and our x was 0.02, we don't have to look, we'd have to know or have to figure out the spring constant if we wanted to solve it the long way, but we don't even have to do that, right? All we have to know is that this is our x, right? This is our x, this is our initial compression, and here's our second compression, right? This is compression 1, this is compression 2, right? So from compression 1 to compression 2, what do you notice? How does the compression change? Exactly, it's doubled. So if we go from x1, right, to then half k 2 times x1 squared, right? Well, we can see then that is half times k, or at least it's half kx1 squared, right? The same half kx1 squared, but we also take 2 squared, so it's times 4, right? 4, because this is 2x1 squared, so 2 squared and x1 squared. So that leaves us with half k x1 squared, and then 2 squared, that's 4. So if you know that half kx1 squared is 3 joules, right? Then 4 times half kx1 squared is 4 times 3 joules, right? And that gives you 12 joules. Does that make sense? Okay. Yep. And someone asked about the relationship between stress and strain. So strain, remember, for strain, like think straining an object, extending it, putting strain on it, then the strain is delta L over L0, right? This is the aspect of strain. Now, stress, right? What was that again? Because I totally forgot. I should pull up my equation sheet because the amount of equations in this freaking chapter is insane. So I know stress and strain, the relationship between them is sigma, this is the stress, times, or is equal to Young's modulus times the strain, right? This is epsilon L, this is the strain, this is the stress. I think it came from this, okay, so it comes from this equation basically. So F is equal to Kx, right? We know that's the spring force. K, actually instead of X, we'll say delta L. That's what we usually define it as instead of X. K delta L. For K, right, for K, we know that to be equal to Young's modulus times the area, the cross-sectional area, divided by the original length of the rod or the object, right? That's our K. Now, if we were to substitute that back in, then we can see that force is equal to Young's modulus times the area over the original length times delta L, right? So Young's modulus times the area over the original length times delta L, right? Now, if we were to divide over the area, right? We have force over area. That leaves us with Young's modulus times the change in the length of the rod, the compression, right? Divided by the original length of the rod. This is our stress. This is our strain, right? Stress, right? You can think about pressure. Like if you're under stress, right, you're under a lot of pressure. And pressure, the units for pressure are pascals or newtons per meter squared. So this force is newtons, areas in square meters, right? Or meters squared. So this is newtons per meter squared. This is pressure. So pressure, right? Think about stress. If you're under a lot of stress, you're under a lot of pressure. And so this isn't pressure per se because stress is different than pressure. Pressure is like the force exerted uniformly over an area. That's pressure. Stress is that same force, but not applied uniformly along the area of the rod. So they have the same units though. So you can just think about, okay, well, if they have the same units, newtons per meter squared, right? That's units of pressure. And so if there's pressure, you're under a lot of stress. If you're under a lot of stress, you're under a lot of pressure, for example. Now, delta L over L naught, right? That's the original length. Here's the compression, right? You can just think about that as being your amount that you stretched or strained, the rod by. And so F over A, we define that as sigma. That's our stress, and then times or is equal to Young's modulus times the strain, and the strain is epsilon L. So hopefully that clears up the relationship between stress and strain. Strain will have no units technically because it's usually just it's meters over meters, so they kind of cancel out, and you're left with usually they give you okay, what's they might ask you okay, what's the stress if you have a strain of 19%? So 0.19 would just be this value right here. So you might say y times 0.19 is equal to your stress, And if you have Young's modulus, you can figure out the stress like that. So, but now it looks like that we can move on to some other problems. So I think number 5 was the first one that someone had a question about. So let me go through them real quick, just look back. So we had 5, 14, 16, 17. So 5, 14, 16, 17, 19, or did we go over 19 already? We already went over 19. 5, 14, 16, 17, and 11, it looks like, and 6. So go back up top here. So 5, 6, 14, 16, 17, 11. Okay. So let's go to 5 first. 5 here is telling us, okay. Yeah, and I can go over some of the written. Hopefully I can get to some of the written, or at least let me know which written ones you guys had a question about. I think someone had a question about written homework, or not written homework, written problem number 2. So I can try and go over that as well. I'll try to blitz through some of these multiple choice. Here it says consider 4 different particles moving in horizontal circles on a frictionless surface in uniform circular motion. Now, as shown in the figure to the right, all are moving at the same speed, for which case is the tension in the string the largest. So, if we're moving in circular motion, what is the tension doing here? What kind of force is the tension giving us? So we know it's a force of tension, but what is the force of tension giving us with respect to circular motion? Yeah, centripetal force, right? So if Ft is giving us our centripetal force, then we know that F tension is equal to mv squared over r, because centripetal force is equal to mv squared over r, right? Where v squared over r is your centripetal acceleration, or AC. AC is equal to v squared over r, right? So mv squared over r is like saying your MAC, and that's equal to your force of tension. So really here, to figure out which one has the greatest tension is just figuring out the relationships. So they told us that the speed is the same. So speed won't factor in because it's moving at a constant speed, right? All moving at the same speed, and it's uniform circular motion. So uniform circular motion indicates that it's constant speed, right? Now, if the speed is all the same, the difference here is in the masses, right? So if I compare all these mass values, well, I want to maximize the numerator, minimize the denominator. So number 3 is the one that gives me the largest numerator with the smallest denominator. Because if I say 2m v squared over r, that's a lot bigger than just mv squared over r, right? It's double, actually. Now, 2m over 2r, so 2mv squared over 2r, well, the 2's cancel out, and so you're just left with mv squared over r. So really, number 1 equals number 4, because the 2's will cancel out. You're just left with m and r, right? Now, for number 2 would actually be the smallest one, because mv squared over 2r, that would be half the amount, or half the tension force. So number 3 is the biggest, because of the, we want to maximize the numerator, minimize the denominator. 2m divided by r. That gives us double the centripetal force. And remember, tension is the centripetal force because it's pointed towards the center. It's pointed towards the center, so Ft is going to give us our centripetal force, because there's no other forces acting towards the center either, right? So, and yes, this session is being recorded. So, that's 5. What was the next one? 6. Hopefully that made sense. I can't remember who asked it, but hopefully that makes sense. So, number 6 is how much energy would it take to bend this microtubule into a circle? So, for energy of bending, right, energy of bending is referring to our elastic potential energy. So, it says here, consider a microtubule, basically a long cylindrical rod, with a length of 1.5 times 10 to the negative 6 meters. So our length, L0, is 1.5 times 10 to the negative 6 meters. Our bending coefficient, BC, is 3 times 10 to the negative 24 joule meters, right? And then Young's modulus is 4 times 10 to the 8th pascals. Now, for how much energy would it take to bend the microtubule, then we have to look at the elastic potential energy. So elastic potential energy, factoring in all these different values like the length and the bending coefficient, it's equal to half times the bending coefficient divided by original length, and then times the angle of bending squared. And the angle of bending here is not in degrees, it's in radians. So not degrees, radians. So make sure midway through the exam and stuff, if you're doing a bending problem, to switch this stuff to radians. Now, they're saying, right, that they want to bend the microtubule into a circle. If they want to bend it into a circle, what's the angle of a circle? .360, right? So 360 degrees. And that would be 360 degrees, right, divided by 360 degrees is 2 pi radians. These cancel out, 2 pi radians. So we use 2 pi radians for our theta here. So we can plug in all this information here, and then we can get 3.9 times 10 to the negative 17 joules. Make sense for part 6? Okay. I think 11 was the next one. Yeah, 11, and then 14, 16, 17. 11 is center of mass, so this is one of the ones that I wanted to go over with. Or go over, my bad. Oh, you keep getting 1.9 times 10 to the negative 17 for this one? 1.9? So you take 1/2 times 3 times 10 to the negative 24 divided by 1.5 times 10 to the negative 6. Put that in parentheses. And then multiply by 2 pi radians. 2 pi squared. It seems like you're getting almost exactly half of what you should be getting. So I don't know if you threw in an extra half there, or I'm not sure. I would double check your calculations, and yeah, I'm not sure, because I did this now. I finally have my graphing calculator back, so like I'm fairly certain of what's going on here. Let me plug it in just to be sure again. 3 times 10 to the negative 24, 1.5 times 10 to the negative 6, and then 2 pi, and then square that. Yeah, the answer should be C. Yeah, you might have either your exponents incorrect or something like that. But that's 6. 11 is center of mass. So if they're asking us, consider the 3 uniform circular disks arranged as shown to the right. The top disk has a mass of 2m, while the other 2 disks each have mass m. Relative to the coordinate axes shown, what is the x-coordinate of the center of mass, right? So we're only looking at the x-coordinate. We're not concerned about the y-coordinate at all. Now, if we look at the x position of the center of mass, the x-coordinate of center of mass, we want to take x1 times m1 plus x2 times m2 plus x3 times m3, and then divide by the masses of all of these combined, m1 plus m2 plus m3. So we can define this one as m1, for example, m2, right, and m3. So if we do x1 m1 plus x2 m2 plus x3 m3 divided by all the masses together, right, well, let's look at our x-axis right here, right? For mass 1 and mass 2, do they have an x-axis position? Are they shifted anywhere right or left of the x-axis at all? I mean, look at the x-axis here, right? This is our x-axis and we're starting at 0 centimeters. This is also along the axis. It's 0 centimeters, right? So like if this is your starting position, if this is your starting position here, this is your x-axis, right? Then x is 0 for both of these, right? This is your starting position here. So anything to the right or anything to the left will give you an x value. But both of them have an x position of 0. So mass 1 should be 0, because if the x position is 0, then it doesn't matter what the mass is. So this is 0 for mass 1, 0 for mass 2, and really the only thing that's contributing any x coordinate is mass 3, because it's directed 10 centimeters away from the x-axis, or 10 centimeters away from the origin, right? So really just x3, m3, right? So m3 here was, it has a position of 10 centimeters away times mass 3, right? Now, we just defined it as just m, right? Now we know that mass 1 is 2m, mass 2 is m, and mass 3 is m. So if we add all the masses here, 2m plus m, we get 4m at the bottom here. So m1 plus m2 plus m3, right? The different masses here, well, the mass here is 2m, here's m, and here's m, right? So 2m plus m gives us 4m at the bottom, right? And we're left with the m for mass 3 at the top here, which is just the m here, right? So the m's will cancel out, 10 divided by 4, and that should give you 2.5. Sound good for number 11 as well? Okay. What was the next one? 16, I think? 16, 14, 16, 17. Okay. 14 is actually very, very simple. I screwed this one up on the exam. I lost points for this one. I was pissed, but I was stupid too. But it's also a very, like, from first glance, a very confusing problem if you aren't reading properly. And they even freaking bolded it, but I think I was just I had a migraine that day and it was just not fun. So I don't want to make excuses, but I wasn't in the best position. I wasn't in the right mind, guys. But really, this is just a matter of like what direction is happening. But you have to look at the right force. So this says a person pushing down on a board, as shown, is keeping their arm in static equilibrium. In order for this to happen, the triceps muscle contracts, providing an upward force on the leftmost part of the forearm. The pivot in this situation is the elbow, right here. What can we say about the torque on the arm due to the board? That's where I screwed up. So all I saw was this arrow. They drew this arrow on the exam. And then I was like, okay, what can we say about the torque? Oh, I was like, okay, all right, cool. So here's the pivot, right? Then if this force is like that, right? If I, think about this as a pencil, right? Then if I pinch the pencil here, not exactly at the eraser, kind of a little bit farther from the end of the eraser, and I just push up on this end right here of the pencil, if I push up essentially at the eraser point, right, then I can see that, well, if I kind of pinch over here and I push upwards like this, then I should see that whole arm or that whole pencil kind of tilt on a clock forward in time, clockwise. And so I made the stupid mistake of saying that it's clockwise, looking at this force. But that's the force, right? Not on the arm due to the board. This force is the force on the arm due to the triceps. The force on the arm due to the board is actually over here, right? And this force, right, if we were to think about this as a pencil again, if this was the tip of the pencil here, then if we were to push upwards like this, we can see that that whole pencil is going to go upwards like this, backwards in time, counterclockwise. So that's why it's B. So this here force is meant to throw you off and trip you up. And that's unfortunately what happened to me. I went full stupid mode on number 14. But it is what it is. Yeah, avenge me. Yeah, I hope like the counterclockwise, clockwise stuff doesn't throw you guys too much off on the exam, because I know it can be sometimes a little bit confusing, but if you just use the pencil trick, I kid you not, I was flipping pencils the entire exam. Like, I think it got annoying, like the person next to me just looked at me, like I was just literally grabbing my pencil and like moving it upwards and downwards. Like, I think De Jong was in there in the exam room at the time, and he thought that like I was like signaling or some shit to like other students, and I was just literally trying to figure out the torque for myself. I just kept moving the pencil up and down like he thought there was like some kind of Morse code with the pencil. But yeah, so careful for this direction stuff. So that's 14, and the next one is 16. So 16 is one of the ones that I want to go over. I don't know. I just want to get this exam over with. That's what I want to do. I want you guys to do well. But two small heavy metal balls, one of mass m, the other of mass 4m, are held over the side of a building and dropped. When the ball of mass m reaches the ground, it has speed v. What is the speed of the ball with mass 4m when it reaches the ground? Right? So the thing is here, we have both at a specific height, right? Starting off here. And they start off from rest, right? Because you just drop them from your hand. So they should have an initial velocity of 0. Now, both of them will have some kind of final velocity. It said for the mass m, it has a speed v, right? How about for the mass 4m? How can we figure out the speed for that one? So the idea here is that there's going to be obviously some change in kinetic energy, some change in gravitational potential energy, right? Because you start off completely at rest, no kinetic energy, no motion, but you have a lot of potential to move when you're in the hand of the person who's throwing you off this hill or building or whatever, right? So there's potential for the ball to move because it has a height, right? H, mgh is our gravitational potential energy, right? Now, like I said, it's better to internalize all the forces because then you don't have to look at angles and stuff like that. You just look at the differences in height, right? So if I internalize all the forces, then I can calculate for my potential energies, and I can say that the energy is conserved and the system is isolated. There's no work, there are no external forces, and the change in energy is 0. That allows me to say, well, W is equal to 0 equals delta E, and then that's equal to change in kinetic plus change in potential, gravitational potential energy, that is. And then based on like what I talked about earlier, it's the idea that whatever energy you initially had, right, that was all gravitational potential energy because there's no kinetic, right? So I started off with all potential, no kinetic because I wasn't in motion yet. And then as I move through the air, there's almost like a perfect conversion rate, right? Whatever energy that's sucked in to kinetic was pumped out of gravitational potential energy. So if I started off at 800 joules, right, and I dropped to 300 joules where there was a decrease in gravitational potential energy by negative 500 joules. That negative 500 joules is going to get sucked out from gravitational potential energy, pumped back into kinetic. So you should see an increase in kinetic energy of positive 500 joules, which makes sense because if K is equal to half mv squared, right? Well, if delta K is equal to half mvf squared minus half mvi squared, well, in order for this to be positive, the final velocity has to be greater than the initial, right? And that makes sense because as you fall through the air, you're going to speed up. So if you speed up, you see an increase in kinetic energy. That increase in kinetic energy, at least from the internal perspective, comes from the fact that the energy from gravitational potential energy was sucked out and pumped back into kinetic. So assuming this equation, assuming everything is internal, then we can say that W is equal to 0 is equal to delta E, and then that's equal to EF final energy minus initial energy, right? And so that then we can see that our initial energies are going to be equal to our final energies. So our initial energies are made up of kinetic and gravitational potential, right? We don't have any kinetic because the object isn't in motion yet. And then for final gravitational potential energy, it should be 0 as well because you're at the bottom of the building or whatever, right? So the height is 0 at the bottom. So if this is mghf, hf is 0, then ugf goes to 0. So whatever initial gravitational potential energy you had gets all converted to final kinetic energy, right? So at the end, you basically only have kinetic energy. So mghi is equal to half mvf squared. This is for ball 1. For ball 2, we can do the exact same thing. We can just skip to this step here, except that the ball is 4 times the mass, right? 4m compared to m here. Now, it's also 4m here, half 4m. But we want to figure out what the speed here is, speed squared here. What is that? What is that going to be? How does that affect what's going on? Well, if we started off with essentially 4 times the energy, 4 times the gravitational potential energy, well, if we want to look at the difference, then we can see here, okay, well, we said that mgh is equal to half mv squared. So instead of saying 4 mgh, we can say 4 half mv squared. 4 half mv squared, right? Well, then we can look at this side of the equation here. We can see that 4, 4, m, half, half. So this v squared should be another v squared here. So that's why the answer is just v. So you can just use this portion right here, substitute it into mgh. So you get 4 half mv squared. 4 cancels out with 4, m cancels out with m, half cancels out with half. You're left with v squared equals whatever speed here is squared. And so v is equal to v, right? V squared is equal to v squared. But yeah. And I'm fairly certain too that you can even, at least I hope I'm not assuming too much information, but think about it as if you like dropped a bowling ball and a feather, right? You know, those different, you know, those types of examples, those quintessential like physics examples, and it tells you like which one is going to fall first or something, and they fall at the same time, right? Well, if they're both released from rest, right? So feather versus ball. Well, if both are released from rest, then VI is 0 for both, right? And then the only thing that's acting on them as they go down is just acceleration due to gravity. So VF is equal to VI plus AT, for example, right? VF is equal to VI plus AT. Well, if they're both at 0 and they're both subjected to negative 10 meters per second squared, right? This is 0, then this is negative 10 meters per second squared. Then both of them should end up at the ground at the same time, right? And if we were to look at like VF squared equals VI squared plus 2AX, or in this case would be kind of Y, right? Then if they both start at 0, they're both subjected to the same negative 10 meters per second squared acceleration, and we figured out what the final velocity is, or actually we figured out or we have the height, for example, right? The change in height. Then the change in height is the same for both. The acceleration is the same for both. The initial starting point or initial starting velocity was the same for both. So they should have the same speed at the end. You can also kind of, you know, do your assumption there, but I'm not one for assuming a lot in physics. I assume when I have to assume, but I think this might take longer, but it's like a surefire way of making sure, like in terms of equations, in terms of things that are definite, you know, that you can see what's going on. I think this is a better way to confirm everything from an equation perspective. But you can literally just say it's the same speed because they're both subjected just to acceleration due to gravity. And so they both start from the same initial velocity of 0 meters per second, right? Then they should kind of have the same velocity at the end. But I don't know. I'm not, like I said, I like to keep it safe. I don't want to assume too much. So I just go with the energy route just to make sure that I can see what I'm doing. But that's 16. Hopefully that made sense. And then there's finally 17. 17 now is very, very simple. It says a stone with a mass of m equals 2 kilograms is tied to the end of a light string, which keeps it moving in a circle. Constant speed of 4 meters per second. The radius of the path is 1 meters. How much work does the tension of the string do on the stone as it makes 1/2 of a complete circle? Well, we know that work is equal to FD cosine theta, right? Well, theoretically, right, if we were wanting to look at the work that's done by that tension force, right, then we can say that the tension force times the distance at which that force is applied, that might be half of the complete circle, right? So if the complete circle is 1 meter, then we can find like not necessarily circumference, because circumference would be the overall like length of the circle, but like half of the circumference. That would be our distance, and then cosine times that angle at which it was applied. That's how we would figure out the work due to tension. However, look at the angle at which it's applied. If this is our force of tension like this, and this is the direction of motion, what is this angle right here? 90, it's perpendicular. What is cosine 90? 0, right? They caught you lacking on this one. So they gave you all this information. They made you look, if like, I mean, I don't know if I saw anyone, I don't remember really if someone actually calculated what this would be technically, but it would be impossible because like you don't have an angle, or at least the angle that you do have doesn't give you any work. So I don't know if someone just took like FD and just like multiplied the force of tension by the like the half of the circumference or whatever, or they did gravity, for example. I don't know. Maybe they got one of these like energies, but it should be 0 joules because cosine 90 is 0, so this whole thing goes to 0. You can't have work done when the distance and the force, or the direction of motion and the force, are perpendicular from each other. So this is just a matter of like checking like who understands the concept of work more than like knowing how to do math. So, but yeah, I think that's all for the problems that people wanted to talk about for the multiple choice. For the written, someone had asked about number 2. I don't know if they're still in the session, but we can go over number 2. There's quite a few people that left, I think. Or never mind, no. Okay, there's like only 3 people that left. That's good. I'm gonna maintain attendance. But for number 2, this is just going back to like the centripetal motion stuff. So it says a 1,250 kilogram car drives at constant speed over the top of a small hill with a radius of curvature of 10 meters. So in the space below, draw a free body diagram of the car at the top of the hill. Label vectors with appropriate subscripts, include coordinate axes. So this is our y-axis. This is our x-axis, right? What forces do we have acting on the car here? Yep. So Fn, Fg, and then if you notice as well, actually, you know what? I will choose a different color to draw these a little bit. So normal force should be like this, and then gravity should be a lot bigger like that. Anyone know why gravity should be bigger? Exactly. So this is a curved path, right? In order to maintain this curved path, we must have a centripetal force, right? And so that centripetal force gives us centripetal acceleration. And so that means basically kind of our like net force has to be centripetal. And if our net force has to be centripetal, then F net is equal to Fc, right? And then the force that is providing that is Fg. So if F net is equal to Fg, essentially, then it's kind of like saying that this Fg has to overwhelm Fn. That's what's kind of going on here. But if we were to write the equation fully, right, because normal force obviously kind of contributes, it's pulling back against the force of gravity, which is giving us centripetal, right? Then we say that F net is equal to Fn minus Fg, and then that's equal to a centripetal force pointing downwards. So we add this little negative sign as well. So what I was saying here, what I was referring to is that like force of gravity is the one that's directly offering any centripetal force or centripetal acceleration. Normal force is holding it back. And so by extension, if normal force is affecting gravity, it kind of has a part to play when determining the centripetal force. And so we say that, okay, well, Fn is pointed positive, Fg is pointed negative, and then the net force, the centripetal force, is pointed along the negative y-axis because it's pointed radially inwards to the circle, right? So there has to be a negative mv squared over r here as well. Does that make sense? So someone had mentioned friction as well. Technically, yes, I think there should be static friction, right? In terms of that's the force that helps propel the car forwards anyway. But I mean, sometimes I honestly just get confused as to why they don't include forces like static friction. So let me just read this over again. Maybe I'm just missing something as to why they're not wanting to include it, or why they're choosing to ignore it. But okay, so I wonder if it has anything to do with the fact that the car is driving at constant speed. So if it's driving at constant speed, then along the x-axis you shouldn't have any net force. Yeah. Okay, so I see it now. Okay. Let me pull that up. The solutions. Okay. So let's see here. So it says, note that one could in principle include horizontal forces, static friction to the right, and both rolling friction. Okay, I see. Yeah, that makes sense, because I was about to say, like, for constant speed, if it's constant speed, there's no acceleration. And so if you had static friction to the right like this, then there has to be other forces to the left that would cancel out. And so in a, real life example, this might be like a different terrain. There might be like dirt or something on the road. And so you would have like some kind of friction opposing as well, or at least like drag and rolling friction, like they said. So they should cancel out to offer constant speed along the x-axis. Yeah, that's why. But I guess also in the grand scheme of the problem, B, C, and D, you're really concerned with centripetal stuff, not necessarily stuff on the x-axis. But yeah. For part B, it says at the top of the hill, the normal force on the car is 9,000 newtons. What is the magnitude of the centripetal force on the car? Right? Now, we know that F net is equal to our centripetal force, and that's equal to Fn minus Fg, right? So this is 9,000 newtons, right? And they gave us the mass of the car was 1,250 kilograms, so 1,250 times 10 meters per second squared, right? And let me calculate that out real quick, and that should give us 9,000 minus 1,250 times 10. And that should give us a centripetal force of negative 3,500 newtons. And they're asking for the magnitude, so the magnitude of Fc is just 3,500 newtons. Now for part C, they're asking us to figure out how fast the car is going. So we know the centripetal force, right? We know the centripetal force. We can relate it to the centripetal acceleration, because this would just be equal to mv squared over r, right? And if we want to keep like our signs correct and stuff, we know that this is equal to negative 3,500, and this centripetal force was pointed downwards, right? So that's a negative mv squared over r. That ends up canceling out anyway, right? We don't factor it in anymore anyway. So then you're just multiplying the radius of curvature over, right? And then you're dividing by the mass and then taking the square root to find out your speed. So 3,500 times your speed, or times your radius, my bad, 10 meters. So this is newtons times 10 meters divided by the mass, which is 1,250 kilograms, and then take the square root to figure out your speed. And then your speed should be, let me calculate it out just to be sure. And the reason why I calculate stuff out as well, even though I have the answer key available, is that there's almost always a issue with the answer key for every single practice. But I think since they used my exam, I didn't think we had any mistakes on our exam. So this should be 5.3 meters per second. And speaking of exams, this that you see here is the exam that I was given. This is the exam that I got. On Google Drive, I've uploaded the practice exam that they gave us, which is entirely different. So you guys have 2 whole exams to practice from. So you're welcome. And yeah, that practice exam has inertia on it, so I would ignore the inertia problems. Yeah. Oh, but angular speed should be on this exam, no? Because that was part of circular motion. Yeah, I can before you guys leave, I will send the Google Drive link here in the chat, and I'll send it on GroupMe as well. The angular speed, angular velocity stuff like that. I mean, we don't have a lot of time left. I don't know if I can cover it, but I mean, it's literally just the equivalence of linear speed, velocity, displacement, and all that. It's just with angles instead of, or like rotational motion instead of linear stuff. So instead of using like meters, kilometers, miles, you use degrees or radians, and usually use radians. Now, there's certain like things like, for example, I think it's your, if I remember correctly, I'm gonna have to review this because I'm not sure, but for your angular speed, right, that's constant over the entirety of the object, regardless of what radius you're at or what distance away you're at from the center of the circle. Now, what does depend on the radius or how far you are from the center of the circle is your linear speed, because that's equal to, linear speed is v is equal to, if I'm, so v is equal to radius times the angular velocity. So if you increase your radius, your distance from the center of the circle, then you get faster. So like, if you look at a bike, I guess on the edges of the bike, there would be a faster linear speed or a greater linear speed compared to the, points towards the center of the circle. Can you also send the notes you're doing on the practice exam solution? Oh yeah. I can send this sheet over, because I did right before this session. I kind of went over, did some like explanations, showed the equations that I use and stuff. For most of them, I think the only thing was like the last two problems or something. I didn't get to the power one, but the power is just changing energy over changing time, which isn't too bad. But bringing it back to this problem number 2, last thing here is that if the car were going too fast, it will be on the verge of launching off the road. What is the magnitude of the normal force at this speed, again, when it's at the top of the hill, right? So if the car is on the verge of launching off the road when it's about to lose contact, the normal force would just be 0, right? Because think about like maximum walking speed too. Like the faster you walk, the lighter you feel essentially. And then like the reason there's a maximum walking speed is if you go faster than that, you're basically going to start levitating. Like you're going to lose contact with the floor. And so here, if you go too fast, right, obviously, like if you think about, if you do a stunt or something, or if you're messing around with your friends, which I've never tried this, but it'd be cool, but also very insane. If you go really fast, like on a hill, then if you don't watch the speed, you're bound to fly, right? So if you go a certain speed where you're on the verge of launching off the road, then the normal force at that point would be 0, because you've lost all contact. Exactly. So normal force should be 0. That's problem 2. Let me see. Really, the star of the show here is problem 4. This goofy ass problem right here is the one I screwed up. Or actually, no, hold up. Let me go to grade score real quick. I think I might have got full points for this one, but not for, no, okay, I did. I messed up C. That's what I messed up. Oh, well, that's not good. Christian's asking about 4C, so let's see if I know my stuff this time around. So, well, okay, so let's see here. So I'll just write down the answers that I have for A and B from the answer key, just so we have like all the information pertinent to solving part C. So we have 25 joules here was the kinetic energy after it's been released from the spring. How far is the spring compressed? It was compressed 0.5 meters, right? Now, when the block encounters the rough patch, how far does the block slide before it comes to rest? So if at this point, at this bottom point of the hill, right, we started off with technically both gravitational potential energy and elastic potential energy at the top here. But remember, with the idea of internalizing all your forces, at least up until here, right, spring potential energy was internal, gravitational potential energy was internal, right, kinetic energy, all of that was internal. So whatever like compression that you had here on the spring and whatever you had for your, gravitational potential energy, that basically got converted into kinetic. And then as you decreased your gravitational potential energy, you increased your kinetic even more. So essentially what's going on here is that maybe you were at this height 3 meters, right? Let's say that gave you a gravitational potential energy of like 300 joules, right? And you also had this spring impart, or at least you were compressing it, right? So it gave you 20 joules of spring potential energy. So you had a total of 320 joules at the beginning when you were at rest, right? Now, that's a total of 320 joules, total energy of the system. When you release the block from the spring went flying, right? So you no longer had any spring potential energy because you're not in contact with the spring anymore. So there was a decrease of 20 joules. Oh, is my screen frozen? Hold up. Okay, there we go. Is it better now? Okay, awesome. So I was saying, like, if you had the spring compressed and that gave you an energy of 20 joules and then you launched the block off, well, the 20 joules had to go somewhere, right? Because energy is conserved, everything's internal. So there was a decrease of 20 joules in the spring potential energy. That all got converted to kinetic, at least for this portion right here, when you're at the top of the hill. So then you went from initial kinetic energy 0 to a final kinetic energy of 20 joules. That's what's going on here, at least for this top portion, right? So now you still have 300 joules because you're still at 3 meters. And then now you have 20 joules, that same 20 joules, it's just that it's not 20 joules of spring potential energy anymore, it's 20 joules of kinetic, right? So you're maintaining your total energy, it's just that it transfers from one type of energy to another. So we got the energy in spring potential energy, that 20 joules, pumped out and pumped back into kinetic, right? To maintain that 20 joules and maintain the overall 320 joules. Now, potential stays the same, at least for this portion right here, this segment, A to B here stays the same because you're at the same height. This is 3 meters, this is 3 meters, this is 3 meters, this is 3 meters, right? Now, once you start decreasing in height, right, you have to maintain that 320 joules still because everything is conserved, everything is internal. The way you maintain it, though, differs because if I started off at the top here at 300 joules, I decreased to 150, right? Well, if I decrease to 150, then to maintain that sum of 320, well, if I had 20 joules up top here and 300 joules of, this is 20 joules of kinetic, 300 joules of gravitational, right? And here I have 150 of gravitational, then I have to have 170 of kinetic. Why? Because if I went from 300 to 150 for gravitational potential energy, 150 joules were sucked out of gravitational and sucked into kinetic. So you see 150 plus 20 is 170, and 170 plus 150, that gives you 320 joules. It maintains the energy. There's no change in energy. Work is equal to 0 is equal to change in energy, right? Energy is completely conserved. This is an isolated system. Now here at the bottom, height is equal to 0. So now you have absolutely no gravitational potential energy, right? Everything is all kinetic here at the bottom. So what we're looking at the beginning of this rough patch is a total decrease in kinetic, right? From whatever kinetic energy here at the bottom until it comes to rest, right? So from here, you might have had that 320 joules of kinetic initial here at the bottom, and at final, kinetic is 0 because, once again, kinetic is half mv squared. You had a certain speed here at the bottom. As that rough patch does work on you, right, then you're going to decrease in speed. You're going to go a lot slower up until you come to rest, which is 0. That's when your v is going to be equal to 0. You're no longer in motion. So when the block encounters the rough patch, how far does the block slide before it comes to rest? Well, like I said earlier, it's better usually to externalize the force of friction, because then you can just look at the work done by friction as opposed to like thermal energy generated by friction. So work done by friction is then going to impart some kind of change in energy, and that's going to only show us that change in kinetic energy, right? So in this case, let's see what other information we have here. Do we have anything about friction? Yes, we do. 0.6 is the coefficient of friction, right? Now, for work done by friction, it should be the frictional force, right? And then that's equal to, they give a friction, or they give coefficient of friction, and okay, so we can probably use then mu times Fn. Yep, because this is kinetic friction, by the way, so because you're sliding the block along this rough patch. So negative F friction, or my bad, not negative, I want to add a negative at the beginning. You'll see why it's negative in a sec. Oh, it's frozen? Okay, let me reshare. Okay, there we go. So friction times the distance at which that force was applied times cosine, and then what's the angle here? If I'm moving this direction, what direction is the force pointing in? It's pointing to the left, right? Then it should be an angle of 180, right? So cosine 180, and that's negative 1. Right, so that gives you that negative at the beginning that I was looking at. Now, there should be a change in kinetic, like we said earlier, right? So instead of like looking at changing kinetic and stuff like that, this delta K and delta U stuff really throws me off. So I just want to look at the change in energy. So work due to friction is equal to change in energy, and that's equal to EF minus EI. Final energy minus initial energy is equal to your delta E. So now we can add initial energy to the work here and get our final energy. So we know our final energy, though. Final energy should be 0, right? Because you don't have any gravitational potential energy, you're not at a specific height is 0, and you've come to rest. So Kf is equal to half mvf squared. If Vf is 0, your final kinetic energy is 0. So this goes to 0. There's no energy once you're stopped, right? You're not in motion or anything like that. Damn it, it's frozen. The whole time was functioning properly, and then it decides to screw up for the last like 5 minutes. Is it better now? You guys see me moving? Okay. So if this final energy goes to 0, then you just add your initial energy to the work done by friction, right? Now the frictional force, like we said earlier, is that mu, right, times the normal force of the block times the distance of that rough patch. Did they give us the distance for the rough patch? I don't know if they did. Or at least, oh, I'm stupid. We're looking for the distance. My bad. We're looking for the distance. And this should be actually minus, because this cosine 180 will give a negative sign here. So minus mu times Fn times the distance, right? So now, is it solving, or is it frozen again? Oh my god. Okay, how about now? Okay. So initial energy minus mu times Fn times the distance that we're trying to figure out, and that's just equal to 0, right? And essentially what we can do even further is just say that initial energy is equal to the work done by friction, right? So what is our initial energy? We keep talking about this initial energy. What is it, right? That's going to be what our kinetic energy here is at the bottom, right? And that kinetic energy at the bottom here is going to be a perfect conversion from what was going on up here, right? So remember I said that we started off with spring potential energy and gravitational potential energy since we were at a specific height. Well, after we launched from the spring gave us 25 joules of kinetic energy. So 25 joules that was a spring potential energy initially, that was all converted into kinetic, right? Now, 25 joules was the kinetic part, but you also had gravitational potential energy, right? So our initial energy at the top of the hill here should equal our final energy at the bottom of the hill. So remember what I was talking about? If you start off with 320 joules here, you end up with 320 joules there. It's just in different forms. So if this was 320 joules where you had 300 joules of gravitation and 20 of kinetic, here at the bottom, 320 joules is equal to just 320 joules of kinetic. This is kinetic, this is gravitational kinetic, right? Because here at the bottom, you no longer have any height. So the key here is to figure out what the initial is at the bottom. And that initial at the bottom, right, was equal to our final from that first segment, right? This first segment here, this is our KF technically, right? Plus UGF. So this UGF, we know that it was 0 because you're at the bottom of the hill here. But you started off with 25 joules of kinetic at the top, and you started off with a specific height. That specific height was 3 meters. The mass of the block, 2 kilograms times 10 meters per second squared, right? That's 20 newtons there, and then multiplied by the height, that was 3 meters, right? So that gives you 60 joules of potential here at the top. So 60 joules of potential at the top, plus the 25 joules from the kinetic, tells us that we had a total of 85 joules at this point right here. So our initial then is 85 joules, because 85 joules at the top, this was our initial and this is our final. 85 joules here goes to 85 joules there. And then for this segment, our initial and final, this is 85 joules, and then this would be 0 joules, because all of the work done by friction will detract 85 joules from the system and cause us to slow down. So we have 85 joules is equal to mu, that was 0.6, I believe, times the normal force, which should just be, if you think about normal force, right? This is Fg, this is Fn, right? Even here, Fg, Fn, this object is not sinking through the floor or anything like that, so Fn should equal Fg. So 2 kilograms times 10 meters per second squared, and then multiplied by the distance, right? So if you solve for all of that, 0.6 times 2 times 10, right, that gives you 12. 85 divided by 12, that should give you around 7.1 meters for your distance. So the idea here is the way I would kind of go about solving it specifically is I would literally, like, to help myself and kind of help the professors and TAs understand what's going through my brain, is that I would just pinpoint segments here. So I can say this is segment A to B, right? And this is segment C to D, right? So I can say, like, energy initial, for example, at B is equal to KB plus UGB, right? Or in a sense, if I wanted to start from the very top, right, then I know that EIA is equal to EFB, right? So whatever initial energy I have at A, that was 25 joules due to the compression of the spring, right? I think that's what it was. Or at least technically it is, right? Based on the idea here that the spring is totally compressed, and then once it's not, you have a lot of kinetic energy, and that kinetic energy was half mv squared, right? And so if we had that speed 5 meters per second when the block is released, well, just based on our understanding of what's going on with energy, if we had this whole thing compressed and the block wasn't moving, then when the spring is uncompressed, then there's no longer any spring potential energy. All of that spring potential energy was converted into kinetic. So you have 25 joules of spring potential energy, basically, plus the 60 joules that came from the gravitational potential energy from being at a height of 3 meters. So that's 85. So at EFB, right, our final position at B here, we should have 85 joules, right? Now from B to C, EIB, for example, to EFC, right? Well, you have that being made up of some initial kinetic energy plus some initial gravitational potential energy, some final, some final. So at the bottom of the hill, this should be 0 because there's no height anymore, right? And then you're just left with Ki plus UGI is equal to Kf, right? So our initial kinetic was made up of that 25 joules. Our initial gravitational, because we were at that same 3 meter height, was made up of 60 joules. So our final at the bottom, so KFB basically, or KFC, my bad. Wow, KFC. Kentucky Fried Chicken is equal to 85 joules. So this is 85 joules. Well, from then we can say that this is kind of saying like EIC is equal to EFD. Then we can say that EIC, right, that's kinetic energy at C plus, well, really, I mean, if you wanted to, you can say gravitational potential energy, but since everything is kind of the same, you can say that this is just that equal to KFD. And then, based on this equation here, we know that EF minus EI, so KFD minus KIC, is equal to the work done by friction. So you just add over the work done by friction. Right, work done by friction plus the initial kinetic energy at point C should give us the final kinetic energy at D. That's the concept of kind of moving back and forth between different points for energies. That's how I would break it up into different points. But yeah, it's a very kind of complex segmentation of the problem, but hopefully that makes sense. I think, Christian, you were the one who asked about that, right? Does that make sense a little bit more now? Okay, awesome. I think some people are heading out already, but I had the Google Drive that I wanted to send you guys, so please stick around for that for a second. Give me 1 second here. I'm gonna pull up the drive. Okay. And we grab the link, copy link, and there we go. I think, oops, hold up. Narrow and muting, there we go. There's the link to the Google Drive. And I think that's it. Hopefully I'll see you guys. I have a session Tuesday the day of the exam. Amit is going to be there from 10 a.m., I believe. He hasn't replied to me yet, but 10 a.m. to around 5:45, basically. Monday, I'm not holding a session. He's not holding a session either. But Tuesday, the day of exam, he's going to be there from 10 a.m. I'm going to be there from around 12:20ish or so. I just have class until 12:15. So I'll be there until pretty much the start of the exam almost. So hope to see you guys there. It's going to be in the fishbowl room in SES. So if you guys have any questions, then please bring them. Please also, for the rest of the night, if you can or if you want to, if you're up for it, still kind of try your best to do more practice problems, study more if you have the time to do so, if you have the will to do so as well. But yeah, the more practice you can get in, the better. And hopefully you guys, do well on this next exam and it goes a lot better. And thank you so much for those who have been coming to the sessions regularly. Thank you for those who came to the session tonight. And thank you for your continued support. So hopefully you guys are benefiting from these sessions, and I can play a part in getting you guys a better grade. So yeah, with that being said, hope you guys enjoy the rest of your night. Goodbye to those on YouTube as well who are going to be watching this later. And yeah, I'll see you guys on Tuesday. Peace.